All right, let's get those eyes up here. We're going to go over these. So what's it called? Thank you. What's it called when we have a function inside of a function? Anyone remember? Composite, yep. Composite functions. So with composite functions, you don't really need to know the name. You just need to identify it and remember how we do it. So composite functions, we said there's one function inside of another. Do we work outside in or inside out? Inside out. That's going to be critical. If you try to look at this whole mess and work outside in, you're going to get confused. It's not going to work. You have to work inside out. So what I mean by that is the first thing you got to do is you got to solve for the inside. The nice thing about, bless you. The nice thing about all three of these is that these inside questions were all chapter 6 questions. Sine of pi over 4. I know there's no unit circle on this slide, but sine of pi over 4, all we have to do is find the angle pi over 4. Sine's our y-coordinate. We figure out the y-coordinate at pi over 4. And that's going to be root 2 over 2. Once we solve for the inside, we plug it back into the outside. So that's what solving for the inside really means. You solve for the inside, and whatever the inside equals, you have to substitute it back into the outside function. From there, now it's just an inverse question. Yeah, it's a chapter 7 question, but you should know how to do these by now. Inverse sine. What's our domain restriction for inverse sine? 1 and 4. What other trig functions, inverse trig functions are 1 and 4? Anyone remember? Cosecant tangent. Yep, they're written on that backboard. Remember, sine and cosine take their sisters with them for the inverse quadrant restrictions. Tangent goes with sine. Cotangent, its sister, they're not on speaking terms. I don't know what happened. Cotangent goes with cosine. The quadrants 1 and 2. So here, long story short, inverse sine, we got to look at quadrants 1 and 4 and see where the y-coordinate is positive root 2 over 2. Where's that happen? Pi over 4, yep. That's going to be our answer.
This question made me second guess myself.
Yep. It's kind of weird, right? Our initial input ended up being our answer. Sometimes that can happen with composite functions. We're going to talk about that a little bit later. It's not a Hail Mary. It's not something every time you see a composite, you should just put in whatever the input was. That's not how you should approach it. But we're going to talk about that in about 10 minutes. So now, this is another composite function. We solve for our inside first. Here it's cosine of 4 pi over 3. Cosine of 4 pi over 3 is what, if we look at our unit circles? Negative 1/2. So we can rewrite this as inverse cosine of negative 1/2. I know I mentioned it when we first started doing composite functions, but please write this step. Because if you got this step right and then you messed up the inverse evaluation, you still get half credit. You still did half of the work. You knew to solve for the inside and plug it back into the outside. So please kind of show the 2 steps when we're working with composite functions. From here, inverse cosine of negative 1/2. Inverse cosine, quadrants 1 and 2 or 1 and 4? 1 and 2, yeah. So we have to look at the top half of our unit circle and see where is our x-coordinate, because it's cosine. Where is our x-coordinate equal to negative 1/2?
2 pi over 3.
Yep, 2 pi over 3. I know I don't have a unit circle up here. Is everyone good on how we got that? Seeing some nods.
I thought it'd be pi over 3. Because, like, I thought you...
What's your, yeah, I understand it. What's your x-coordinate at pi over 3?
1/2.
Yep. What's your x-coordinate at 2 pi over 3? Yeah, which one are we looking for? Yep, if the sign matters. And that happens a lot. That happens a lot with these inverses. You got to be keyed into the sign. Positive means we're going to be in quadrant 1. Negative means we're going to be in quadrant 2 or 4, depending on the trig function. So finally, number three, first thing we got to do is solve for the inside. Tangent of negative pi over 3. What's the coterminal angle to negative pi over 3 that's on our unit circle? Remember, coterminal angle means the angle that's at the same exact point.
5 pi.
Yep, 5 pi over 3. If that was confusing you, or you're still a little bit lost on these negative radians, first thing I'd suggest is kind of go back through the lectures and get more practice with it. The second thing I'd suggest is kind of looking at it like this. Tangent of negative pi over 3. Well, we know positive pi over 3 is going to be right there on our unit circle. Negative pi over 3 is going to be the negative reflection of positive pi over 3. So negative pi over 3 is going to be right there. And that's one thing that you can always kind of depend on with your negative radians. They're just going to be the negative reflection of the positive radian. So here, whether you evaluated a tangent of negative pi over 3 or tangent of 5 pi over 3, we know tangent's y over x. You saw that your y was negative root 3 over 2, and your x was 1/2. Give me a thumbs up if you got those coordinates. Yep. So if you flipped it, you would have got the same answer. Your 2's would have canceled out. So then you would have been left with negative root 3 over 1. I just dropped the 1 in the denominator. So negative root 3 would have been the answer to the inside. This was a composite function, so we had to plug the answer for our inside into the outside. The way that would look is inverse tangent of negative root 3. Negative root 3, the way I like to think about inverse tangent, if you're someone who wants to plug in the points, that's fine. The way I like to think about it is root 3 greater than, not paying attention to the negative sign, is root 3 greater than 1 or less than 1? Oh, greater than 1. The way we know root 3 is greater than 1 is root 3 is greater than root 1. That makes sense. The square root of a bigger number is going to be more than the square root of a smaller number. Square root of 25 is 5. Square root of 9 is 3. The bigger the number is inside the square root, the bigger the answer is. We know that's true except for 1 and root 1, because square root of 1 is just 1. So just by kind of extending that inequality out a little bit, we see that root 3 is bigger than root 1. So here, even though it's negative root 3, we know that that slope is going to be steeper than the slope of 1. Now, if you're like, Mr. Suchi, how's that help me? This is how. So we're looking in quadrant 4. Kind of a bad drawing, I'm sorry. But we know the slopes of 1 or negative 1 are always going to split our quadrant in half. It's going to be at pi over 4 or negative pi over 4. The slopes of 1 or negative 1 are always going to split our quadrant in half. Here, we said root 3, not paying attention to the negative, was greater than 1. What that tells us is that our slope is going to be steeper than the slope of 1. Steeper, one way to think about it is a roller coaster, or a hill, a sledding hill. Which one would you go down faster? One that's very steep or one that's not as steep? Yep, very steep, yep. So when we're saying that it's greater than 1, we're saying that it's steeper than 1. The same applies to the negative. We're looking for the slope that's steeper than negative 1. We would go down that sledding hill faster than we would go down that sledding hill. That's just kind of one way to think about it. So now we're back at the same point. That same point is going to end up being negative pi over 3. Now, if you were to ask me, Mr. Suchi, does 5 pi over 3 work? I would say, yeah, for some partial credit. Remember, this is a composite, but when we rewrote it, it was just a straightforward inverse trig problem. When it's a straightforward inverse trig problem is when we have to qualify our answers within the domain restrictions. So once again on that back board, if we're trying to answer an inverse tangent, it has to be between negative pi over 2 and pi over 2. Any questions with 1 through 3, how we got these? Yeah?
How do we get from negative root three to, because I understood the negative power of the three was the same as 5 power of the three. But how did we get from the negative root three back to the negative power of the three?
Yep, so inverse tangent, the way we kind of evaluate that is you have to find the point that's going to give us this value. The point, and that's when I was talking about the steepness, the point that's going to give us the tangent value of negative root 3 is going to be right there on our unit circle. It's going to be right there. It's going to be the point that's slightly steeper than the point that would give us the slope of negative 1.
So it's negative power of three or 5 power of three, or is
It's,
it negative power?
to get full credit, you have to put negative pi over 3.
And that's what we wrote on the board over there, if you see, for the inverse trig, quadrants 1 and 4, your answer has to fall within that rectangle. So for sine, cosecant, and tangent, your answer has to be between negative pi over 2 and positive pi over 2 to get full credit.
So now I know we just spent a good amount of time, maybe 10 minutes, talking about these questions. But let's pretend we didn't. Let's pretend we were just looking at these questions kind of with a fresh start. What do we notice as a similarity between questions 1, 2, and 3? Not our answers, just the questions. What? They're all what?
Is it radicals? Is that what they call it when they have the
Radians. Yep. Yeah, they're all radians. That's a great. Thank you, G. That was a great observation. Our initial inputs are all radians. Kind of one way to think about that also is the inverse functions were all on the outside. The normal functions were all on the inside. Any other observations? Yes. That took period 1 a couple minutes to find. Yeah, it's inverse sine of sine. It's inverse cosine of cosine. It's inverse tangent of tangent. Now, this doesn't always have to happen with our composite functions. We could 100% throw at you an inverse sine of cosine or an inverse cosine of tangent. We can mix them up. That doesn't mean we have to. In fact, when these functions kind of have the same base, and what I mean by that is inverse sine of sine or inverse cosine or of cosine, when the inverse and the normal function match up, that needs to kind of perk up our ears, and we're going to talk about that. One of the questions we had earlier was, how often is our initial radian going to be our final answer? And now we're going to kind of explain why that happens and when that happens. So here, if we remember our answer was pi over 4. For number 2, our answer was 2 pi over 3. And for number 3, our answer was just negative pi over 3. So which questions was our initial input equal to our answer? 1 and 3. Can anyone spot the reason why 2 didn't work? Yeah, so 4 pi over 3. It's greater than 1. Yeah. So what happens when a radian is greater than 1? Can it be in quadrant 1 or 2? No. What quadrant is 4 pi over 3 in? 3. Inverse cosine, does that work for quadrant 3? No. What quadrants does inverse cosine work for? Oh. 1 and 2. You got to be good on that. Inverse cosine is 1 and 2. If you're still struggling with remembering our restrictions, you got to go back, make an index card, something. It will throw you off on your quiz if you don't know. Inverse cosine is 1 and 2. 4 pi over 3 is not in quadrant 1 or 2. It's in quadrant 3. Because of that, our final answer was not going to be the same as our initial input. Now looking back, what quadrant is pi over 4 in? 1. Yep. Is quadrant 1 within our domain restriction for inverse sine? Yes. What quadrant is negative pi over 3 in? 4. What's the domain restriction for inverse tangent? Yep. So negative pi over 3 is within our domain restriction for inverse tangent. And we see when that happened, our final answer was the same as our initial input. So here's how we can kind of check for the shortcut. When we can check to just rewrite our answer as the initial input. This is what has to work. First things first, the two functions have to have the same base. All three of these have the same base. If it was inverse cosine of sine of pi over 4, we aren't playing with it. Because these two do not have the same base function. Nod with me if that kind of makes sense. They have to match up. Inverse sine and sine. They have to give us a pair. Inverse cosine, cosine. Inverse tangent, tangent. If that's true, then you just have to do one more quick check to see whether or not our shortcut applies. And that quick check is just identifying what quadrant our input is in. If that quadrant matches up with our domain restriction for the inverse of that function, and I know that's wordy, but you just saw what that means, then we can use the shortcut. So here, inverse sine of pi over 4. Okay, it's the same function. Shortcut might work. From there, okay, let's see what quadrant this input's in. We already said it. Pi over 4 is in quadrant 1. Since it's in quadrant 1, I look back and see, okay, what quadrants is inverse sine again? Oh, it's quadrants 1 and 4. We have a winner. Once I see that, I don't have to do any more computation for this problem. All that work that we did when we were going over, yes, that's still how you solve every other composite function. But here, you can just rewrite the input as your answer. Any questions on that? Write down these 4 questions real quick. Write fast. I'm giving you about a minute and a half. Don't start solving, just write them down. What's the similarity we notice between all 4 of these problems? Yeah, it's the same base, right? It's the same base function. Inverse cosine of cosine, inverse sine of sine. That tells us that we can check for the shortcut on all 4 of these. Looking at question 1, the first thing I have to do is I'm checking for the shortcut, is I have to see, okay, the same base function, let's look at that input. That input, I have to figure out what quadrant it's in. What quadrant is negative pi over 6 in? 4. Yep, the way we can see that, we know negative pi over 6 is a negative reflection of pi over 6. So you can find pi over 6, straight line down, and we see that 11 pi over 6 equals negative pi over 6. So we're in quadrant 4. What's our domain restriction for inverse cosine? So can we use our shortcut? No. That's all I want you to write down. No SC, no shortcut. If you want extra practice solving composite functions, be my guest. do that problem later. We're not going to worry about it now. Yep.
Does not exist.
Why isn't it? Because it does exist. Just real quick, don't write this down. I'm just showing Karma that it does exist. Cosine of negative pi over 6 is 3 pi over 2. Inverse cosine of 3 pi over 2 is positive pi over 6. Positive pi over 6 exists. So that's a great question. Mr. Succi, what happens if I check for the shortcut and it doesn't work? Well, then you just have to buckle up and solve your composite function the way we've been solving it for a week. Inside out. The same way we did those bell work problems. All right, looking at number 2. What quadrant is pi over 4 in? 1. Remember, our domain restrictions, every single one includes quadrant 1. So if we're in quadrant 1, we're always going to be able to use a shortcut. As long as these two functions, the two functions are the same base. It's negative sign, or not negative sign, inverse sign and sine. Here, both of our steps are fulfilled. Same base function within the domain restriction. So that's just our answer. Are we kind of seeing why this is a beneficial shortcut? How it can save us a lot of time? All of a sudden, a minute question goes down to maybe a 15-second question.
How many questions are on the class?
I'm not sure. I think Miss Bryant took off a couple. I was out the last couple of days, so I can't give you a firm number. All right, so number 3, inverse cosine of 11 pi over 6. This is where you got to be careful. Don't get kind of lulled to sleep by thinking, oh, cosine, whenever it's positive, it's within cosine's restriction. Because what quadrant is 11 pi over 6 in? 4. Is that within the inverse cosine restriction?
No.
Nope. So even though these were the same base function, our shortcut is not going to work for number 3. It is not going to work. And one thing I'd like to add, the shortcut's great, and it's going to save you some time if you know how to use it on your quest. But it is not something to do just kind of as a Hail Mary. I don't feel good about composite functions. I know I'll get some right by doing it. If the shortcut doesn't apply and you don't show any work and you just rewrite the input as the output, you're not going to get very much partial credit at all. You would get more credit by just solving it the way we solve composite functions. Now the shortcut is something pretty simple to check for, right? Same base function within the restriction. But if all of a sudden I see someone using it and it's on a question that looks like inverse sine of cosine of pi over 6, we should know right away, sorry for the sloppy handwriting, we should know right away that that's not a candidate for the shortcut. So if you try to use the shortcut there, you're not showing me that you understand the shortcut or really composite functions, and it's going to be hard to give you any credit. Now, when you identify somewhere where it does work, use it. Use it. You might even have to use it, and we'll get to that on number 4. But don't just use it as a Hail Mary. Let's run through these composite questions and get half my credit. Don't do that, please. So finally, inverse tangent of 3 pi over 8. Let's pretend that we didn't know the shortcut exists. Let's go back in time about 20 minutes. Tangent of 3 pi over 8. If we were just trying to solve for the inside, where would we look on our unit circle? Quadrant 1, yes. But is there a specific point? Is it coterminal to anything on our unit circle? Nope. There's nothing on our unit circle that has a denominator of 8. What we do know is that 3 pi over 8 is in quadrant 1. How do we know that? It's less than 1?
It's less than half.
Less than half. So make sure we're eyes on the board for this fact right here. 3 over 8 is less than 1/2. That's just a fraction inequality. That makes sense. We also know 3 over 8 is greater than 0. Yeah, there's a pi in there, but that doesn't really change our fractions. We know that 3 pi over 8 is going to be between 0 and pi over 2. What that tells us on our unit circle is that that's going to be in quadrant 1. Not if that makes sense. We know 0 radians is right here. We know pi over 2 radians is right here. If our angle is between 0 and pi over 2, it's got to be somewhere in quadrant 1. We don't know where, but we know it's in quadrant 1. Now kind of resetting, the shortcut does exist. These are the same base functions. So now we just have to check to see if our input is within the domain restriction. Is quadrant 1 part of inverse tan's domain restriction? Yes? Yeah, what's inverse tangent's domain restriction? 1 and 4. Yep, so 3 pi over 8, we don't know where it is in quadrant 1, but we know it's in quadrant 1. That's good enough for us. Oh, there we go. That is good enough for us. We can just write this one as 3 pi over 8 and be done with it. What?
So that's like an educated guess.
It's a firm answer. We know with our shortcut that our answer